Okay, so yeah, so what was that actually? So Carnot's theorem, uh, it states that of all heat engines operating between a given constant temperature source and a given constant temperature sink, none has a higher efficiency than a reversible engine. Okay, so here in this diagram you can see two engines. One is the irreversible engine or normal engine, normal heat engine, and another is the reversible heat engine. Okay, so we have finally proved that the efficiency of this reversible engine, it is maximum. Okay, so in between two constant temperature source, the reversible heat engine will be having the maximum efficiency. Understood? So this was the Carnot's theorem, and we have proved by violating the Kelvin-Planck's law when we consider that efficiency of this heat engine will be greater than this one. So finally, with this diagram, you can prove that thing. Okay. Then second thing is the corollaries of Carnot's theorem. So what was the corollaries of Carnot's theorem? The efficiency of all reversible heat engines operating between the same temperature level is the same. Okay. Suppose this is one reversible heat engine and this is another reversible heat engine. I think my screen is visible to everyone. So this efficiency of this heat engine and this heat engine will be same if both the engines are reversible heat engine. Okay. The next one is the efficiency of a reversible engine is independent of the nature of or amount of working fluid undergoing the cycle. So it doesn't matter whether a heat engine it is operating by a certain kind of fluid and another heat engine it is also running by certain kind of fluid. So the efficiencies of the reversible heat engine will not be dependent on the working fluid. Okay, because it generally happens that for refrigerator, okay, suppose refrigerator will be also a heat, okay, heat pump or heat uh, uh, this one heat cycle in engine or refri pump you can say. So those refrigerator efficiencies or cops, okay, coefficient of performance, so it depends on the fluid, okay, or the regulatory component on which the efficiency will depend. Okay, means it always depends on the regulatory fluid. Okay, but here reversible refrigerators or reversible pumps or reversible heat engines will not depend on uh, the quantity, okay, or the amount of matter or the amount of working substance. Understood? So it will be always same. Okay, so here one thing I want to say you that, so this is the reversible engine. So we have taken this example before also. So when the reversible engine was producing some efficiency, so the definition of the efficiency will be what? WB upon Q1B, isn't it? Output upon input, this is the input, this is the output. So this will be maximum, while when this will be minimum, Q2B will be minimum, isn't it? Because WA directly depends upon this minus this. So if this is minimum, then only WA will be maximum, okay, or WB will be maximum. This is WB, isn't it? So efficiency will directly depend on this ratio WB upon Q1B. Okay, so here for reversible heat engine always this will be minimum. Understood? So if you just take that whether this one, if you are just asked whether this will be minimum or this will be minimum, then you need to say that because these two engines are operating in between the same temperature source, that is why Q2B will be minimum. Okay, then only this efficiency will be maximum in comparison to this engine. Understood? So on the principle of this Carnot theorem and corollary, so today we will be solving two problems. Okay, then only your concept will be clear to you, and we will be using these formulas also. So you need to commit to this, commit to your memory all this formula. So here you can see for a reversible heat engine, the efficiency is given by eta maximum, because reversible heat engines are having the maximum efficiency. So eta maximum or eta reversible, okay, same thing, will be equals to 1 minus q2 upon q1. So here it is said as reversible, okay. So 1 minus q2 upon q1, and from the absolute thermodynamic scale, so we can write for reversible engine, this q2 by q1 will be equals to t2 by t1, okay. So if you just uh, uh, this one, if you just convert this formula to, you will get this type of formula, okay. So this is also the same representation of the efficiency, reversible heat engine efficiency or maximum efficiency of a reversible engine, okay. So it is observed here that as T2 decreases, what I actually told you, as T2 decreases, the T1 will increases, okay. So efficiency of the reversible engine will also increase, understood. So here you can say that if q2 decreases, okay, then efficiency will increase. Same way you can say that as, because by temperature, absolute thermodynamic temperature scale, this ratio actually valid, q2 upon q1 is equals to t2 upon t1. That is why you can say that for reversible heat engine, the efficiency will be maximum as T2 will be minimum, okay. So since eta is always less than unity, it should always be less than unity. So T2 is always greater than 0. T2 cannot be 0, otherwise it will become a PMM2 machine, okay, and it should be having some positive finite value. Next one is the reversible refrigerator. So COP of the reversible refrigerator is given by Q2 by Q1 minus Q2. So for heat engine, it is W uh, work done, and for COP of refrigerator, it should be Q2, isn't it? Because we need to uh, abstract, we need to subtract heat from the freezing chamber, isn't it? So this is our requirement. So Q2 is our requirement, we need to cool some chamber, okay. So q2 by q1 minus q2, so this one you can replace by this t1 minus t1 by t2, okay. So COP of the reversible refrigerator will be t2 by t1 minus t2, okay. So this one you need to remember, okay. So similarly for a reversible heat pump, so here it will be T1, okay, instead of this T2, here it will be T1, and the expression will be T1. So all these three formulas you need to remember, means all these things you need to remember. Then only you will be able to compare, okay, the efficiencies and the COPs of the heat engine, as well as the coefficient of performance of a refrigerator and heat pump, okay. So now I am going to take two problems, okay, then only we will be able to solve, or we will be able to learn this topic uh, in depth, okay. So the question is, just go through the question very carefully. A cyclic heat engine operates between a source temperature of 800 degrees centigrade, okay, and a sink temperature 30 degrees centigrade. So what is the least rate of heat rejection per kilowatt net output of the engine? Okay, so it is given that a reversible, that a heat engine, normal heat engine, it is given, okay. So it works in between a source and the sink, just like our previous example, okay. So one source will be there, one sink will be there. So the source will be having some temperature, it is having a temperature of what, 800 degrees centigrade. So we need to convert this degree centigrade into Kelvin, okay. So 800 plus 273 Kelvin, okay. So then you will get the value of this temperature of the source, and the sink temperature is how much, 30 degrees centigrade. So you need to add 273 Kelvin with this sink temperature, then you will get the sink temperature, okay. So what you are asked, what is the least rate of heat rejection? So you are asked that the heat engine is giving or it is releasing least heat, okay. So when a heat engine can give out least heat, so when the heat engine will be a reversible heat engine, I told you, isn't it? So when q2 will be minimum, then only that will be a reversible heat engine, understood. So what is the least rate of heat rejection per kilowatt net output of the engine? So we will see what is the per kilowatt net output of the engine. So for this question, so how we will proceed, so we will first make this diagram, Okay, so then only you will be able to means see what are the things given and what are the things you need to find out and what is the concept behind this problem. Okay, so it will be a reversible heat engine because the rate of heat rejections will be minimum, isn't it? Because if this is minimum, then only this ratio will be maximum, W by Q1. Okay, because W is what, Q1 minus Q2. So Q, when Q2 will be minimum, this value will be minimum, this W will be nearly equals to Q1, isn't it? But Q2 is not equals to 0, what we have actually read a few minutes back. Okay, so W will be equals to Q1 by Q1. Okay, but it cannot be 1, that is why its value will be little less than 1. Okay, so here, so this is the exact figure. So this is 1073 800 plus 273 Kelvin, so 1073 Kelvin. This is the source. From the source, the heat engine, cyclic heat engine, reversible heat engine will take heat Q1. Okay, so and we don't know what is the amount of heat Q1, we need to find it out. Okay, and here this Q2 amount of heat it has to reject, otherwise it cannot produce W amount of work done, otherwise it will be a PMM2 machine. Okay, it will violate Kelvin Planck's law. Okay, so here some amount of heat, very minimum amount of heat it should reject, otherwise it will not be a reversible heat engine. Okay, so Q2 amount of heat it is rejecting, and sink temperature is how much? T2 is equals to 303 Kelvin. Okay, and I think up to this much your points are clear. Okay, and if it is not clear, then you can ask me. Understood? Okay, so here what was the efficiency? We know by formula that efficiency of a reversible heat engine is what? Eta reversible or eta maximum is what? 1 minus T2 upon T1, isn't it? So what is eta? So 1 minus this one, what is T2? So T2 is what? This is sink temperature. So 30 plus 273, because 30 is given, so you need to add 273 Kelvin. Then 800 plus 273. Okay, so if you just calculate this value, you will get that 1 minus 0.282. Okay, so it will be 0.718. Understood? So this one will be the efficiency. Okay, so it is not equal to 1, isn't it? So it is less than 1.718, and in percentage it will be 71.8%. Understood? So now what you can find out? So you can find out the heat input. Okay, you can find out the heat input. So what will be the heat input? So here it is given that what is the least rate of heat rejection per kilowatt net output of the engine. Okay, so per kilowatt. So we have taken that W will be Q1 minus Q2. So per kilowatt we will be finding what is the amount of this one. Okay, this heat rejection means Q2. What is the amount of Q2 on this 1 kilowatt? Means Q1 minus Q2 will be 1 kilowatt, because we are asked to find out upon per kilowatt, isn't it? So W equals to Q1 minus Q2 equals to 1 kilowatt. So eta maximum we have found to be 0.718. So what is eta maximum? This is W net upon Q1, because this W net or W upon Q1 will be the efficiency. So what is Q1 then? So eta maximum or W net upon eta maximum. So W net is what? 1 kilowatt. Okay, because it is given in the question to find out Q2 upon W. Okay, so it is 1 kilowatt. So 1 divided by 0.718. So this will be your Q1. Okay, but you are asked to find out what is the minimum amount of heat rejected per kilowatt of the work. Okay, per kilowatt of the work output of the engine. So we need to find out the heat rejection, that is Q2. So Q2 will be what? Q1 minus Q2 is W. Okay, so you can find out Q2. Q2 will be Q1 minus W net. Understood? So Q1 minus W net. So 1.392 minus 1. So 0.392 kilowatt will be the minimum amount of heat which is rejected to the sink. Understood? By this heat engine. So this way you need to actually find out all the things whatever you are asked to find out. Okay, you may be asked to find out Q1, you may be asked to find out Q2, or you may be asked to find out T2 or T1 okay, or efficiency or work done, whatever it is, but the game is on the basis of this diagram. Okay, so that is why you need to know how to draw this kind of diagram. Understood? Now we will be taking another example. So I have taken this example from PK Nag book directly. So here, one domestic food freezer maintains a temperature of minus 15 degree centigrade. Okay, because this is a freezer, so it will be maintaining one chamber at minus 15 degrees centigrade, isn't it? So the ambient air temperature is 30 degrees centigrade. Okay, so here this is the freezer, freezing chamber. So here 273 minus 15, so you will get 258 Kelvin, because you need to convert the units to Kelvin. Okay, then only your calculations will be simplified, otherwise it will be wrong. Okay, so freezer T2 is 258 Kelvin. Okay, and from here Q2 amount of heat it is rejecting, okay, taking out, otherwise you cannot make this chamber in freezing temperature, okay, or in this amount of temperature, minus 15 degrees centigrade temperature, isn't it? So when you will give out heat from a system, when you will take out heat from a system, then only that system will be cooler, isn't it? So Q2 amount of heat which is rejected or which is taken out by this refrigerator, that is why this is a freezer or this is a refrigerator, and this is cyclic refrigerator, isn't it? Because normally heat engines, these cyclic refrigerator pump, these operates on this cyclic process. Okay, so cyclic refrigerator. And to do so we need to do some work, because if you do not do work on this refrigerator, so you cannot transfer heat from a lower temperature source to higher temperature source. Okay, so by second law of thermodynamics, Planck's statement, so we have actually proved that one. Okay, so from lower temperature to higher temperature, naturally heat doesn't flow, isn't it? So to flow that heat, so we need to do some work from, okay, from the outer side, isn't it? So this amount of work it is done, means this amount of power it is introduced to the refrigerator, and that is why this Q2 amount of heat it is taken out, and this Q1 amount of heat it is rejecting. Okay, so at the same time it should operate in between two sources, isn't it? So this one is the first source, this one is the other source or sink, whatever you will say. Okay, so from here heat is taking and from here it is rejecting, otherwise this W will be obsolete. Okay, what it is given actually, so this freezer temperature is given, so it is 258 Kelvin. Then ambient temperature, this temperature is given, it is given as 30 degrees, so 273 plus 30 you will get 303 Kelvin. Okay, so this is the diagram. So work has to be done, so Q2 amount of heat has to be rejected by this chamber to the engine. Okay, so this amount of heat it will be abstracting and it will be delivering Q1 amount of heat, isn't it, to the ambient, okay, or to the surroundings. Understood? Now you are said that it is said that if heat leaks into the freezer at the continuous rate of 1.75 kilojoule per second, means heat it is coming as 1.75 kilojoule per second, because it is running in a cycle. So at the last of the cycle, so this amount of heat it is coming to this freezer, 1.75 kilojoule per second. Okay, so this much amount of heat it is coming to the freezer. So same way this freezer needs to give away this amount of heat to the engine, okay, to the refrigerator, isn't it? So this amount of heat needs to be extracted from this chamber, then only this will be cooled at 258 Kelvin. Okay, so ambient temperature this one, so the refrigerator cycle removes heat from the freezer at the same rate at which heat leaks into the system. Okay, so from this to this chamber, so this amount of heat it is leaking, and from this chamber this Q2 same amount of heat has to be rejected, otherwise you cannot maintain it in this temperature. Okay, so now as because this process, okay, so we'll be taking this formula, okay, Q2 by T2, so Q1 by T1. Okay, so Q2 is given, so we need to find out Q1, isn't it? So what is the least power necessary to pump this heat out continuously? Means we need to find out this much power by which this Q2 amount of heat has to be pumped out from this chamber, otherwise this Q2 amount of heat it is entering, so we need to extract that same amount of heat with the expenditure of this work. Okay, isn't it? So This will be only found out when this q1 amount of heat will be known, because q2 is already known, this much it is given. So w depends on q1 also. Okay, so it depends on q1 and q2. So if we can somehow find out this q1, so we will be able to find out the power, okay, external power necessary to pump this heat out continuously. So I think this diagram is clear to you now. Okay, and from this relation q2 upon t2, q1 upon t1, so we can find out the value of q1, because q2 is given, t2 is given, t1 is given. So what is q1? So q1 will be this much. Okay, so from this relation, so all the three parameters are given. So to find out q1, so you need to multiply t1 by q2 by t2. Okay, so here you will get the value of q1. And what is w? So w will be simply q1 minus q2. Okay, so from here, so you will be able to find out what is the power which is necessary to actually pump out the heat, okay, this much of heat from the chamber. Okay, so w will be equals to q1 minus q2, and this much of power will be needed, okay, to subtract heat or to remove heat from this chamber and to maintain this chamber at minus 15 degree centigrade. Okay, so I think I have cleared, okay, all the
Yes,
concepts
sir.
regarding this Carnot's theorem, okay, or Carnot's principle, these corollaries. And if you have any doubt, okay, so you can ask now. I think the things are now a little bit clear to you. Hmm?
Yes,
So
sir.
can I ask? Yes, Emiel, Parmiki, Rishikesh, Teja, anyone. If you want to share anything, means you are finding some difficulty or you are just not understanding few of the things, you can say, okay, you can put your views. I will try to come up with some this one means some positive vibe, okay, so that we can sort all those problems. Yes, you be frank. Please tell me if you have any difficulty. Okay, if you are having any kind of problem in understanding this topic. Okay, you can share. I'm giving you 2-3 minutes. Yeah, anyone? Partha, Partha, do you want to share anything? No, Sal. Yeah, Partha. Partha. Yes. So how you are finding this course, Partha? Is it fine? And I have shared the assignments also. Have you gone through those questions? If you are finding any difficulty, you can let me know. Okay, but you need to
Sir.
try. Yes, you need to try, because as it is an assignment, so you need to try yourself. Okay, very hard. Then only you will get some other concepts apart from this class also. Yes, Emiel, my voice is clear.
No, sir. Yes, sir. Your voice is clear,
Okay,
sir.
okay. So I think some of the concepts now you are able to grab. Okay, because see, this is not a very newer thing actually to you. This thermodynamics, and by the grace of God, we have actually given. We are given another 1 month. Okay, so we will be finishing each and every topic by understanding in its depth. Okay. So Rehan,
Yes, sir.
yes, Parmiki, anything you want to share?
Excuse me, sir. Why,
Yes.
sir, in the first question, sir, why Q1 minus Q2 is equal to what?
Okay, why? Wait, just first question. I think my screen is visible to you,
Yes, sir.
Parmiki. Uh,
Yes, sir.
which one? Which you are asking actually? Why Q1 minus Q2 is
Q1
one?
minus Q2 is equal to 1, sir.
Okay, so in the question, just you see the question. What is the least rate of heat rejection? Okay, per kilowatt net output. So it is given as per kilowatt net output. Okay, so per kilowatt net output means what? 1 kilowatt. Understood? That is why it is
Yes,
1
sir.
kilowatt per kilowatt. So on this per kilowatt net output, so we will be calculating this heat rejection. Okay, so if everything is on this scale, so whatever you are going to find out, so on this w value will be it will be compared. So q2 will be simply this one, means this much uh, This is the rate of heat rejection per kilowatt, means in 1 kilowatt work output, so this kilowatt will be the heat rejection. In 2 kilowatt work output, so this multiplied by 2 kilowatt will be the heat rejection. Understood?
Okay, sir.
Okay. Yes. Anyone wants to share anything? Rishikesh Bosumatari?
No, sir. Understood, sir. Everything.
Understood, no? It is actually not that tough thing, but the thing is that you need to construct, you should know how to construct this diagram actually,
Yes, sir.
okay? And how the relations actually, the formula for the efficiency, actually some concepts are there. So those concepts you need to learn, okay? And you need to make the notes in a copy, okay? In a khata, so that all the things are systematic, okay? So thank you, dear students. Now you can leave this meeting if you want, okay? So thank
Thank
you.
you, sir.
Yes.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir.
Thank you, sir.